All right, so this is section 6.8. So I know it might seem like, depending on when we're doing this, it's in a strange order. Um, but technically, this is kind of a lesson that we can kind of put anywhere once we've gotten to a certain point. This is what is called L'Hôpital's rule. Yes, I'm aware it's spelled L apostrophe hospital's rule. It's pronounced L'Hôpital. I'm assuming it's a French. Actually, I know was a French mathematician. L'Hôpital's rule. And what L'Hôpital's rule is kind of a way to make doing certain limits easier. And you're going to find that this is going to make, well, again, doing certain things, like some of the ones that you see here, specifically like number 3 especially, it's going to make it a lot easier. So we're going to review kind of some of the limit stuff that we've done, because we haven't really done limits in quite some time. So for something like number 1, if we want to take the limit as theta approaches 0 of cosine of theta tangent theta divided by theta, if you were to plug 0 in for everything, on the numerator you would get cosine of 0, which is 1, times tangent of theta, which is 0, over top of 0. We know that the numerator would give us 0, the denominator would give us 0. So in that case, we know that there's probably some other way to simplify this. So we could rewrite this as the limit as theta approaches 0 of cosine of theta times, now we can rewrite tangent as sine of theta over cosine of theta, all divided by theta. The nice thing there is that the cosines go away. And now we're left with the limit as theta approaches 0 of sine of theta over theta. Now, this is one of those special ones that I told you guys that you just kind of had to know for right now. L'Hôpital's rule will make this much easier to deal with. But for right now, if you recall, that is a special limit, and the limit of that one was 1. Okay, and if you don't remember that, I'm going to show you the shortcut to this, not in not too distant future here. Number 2, L'Hôpital's rule also will work with this one when we get to it. But for right now, if you were to plug in 3 in the numerator and denominator, once again, you would get 0 on top and 0 on the bottom, and that can't happen. But again, that creates usually a hole in the graph, so there most likely is a limit. So in order to do this one, we would have to use the multiplying the top and bottom by the conjugate, which was multiplying by the same 2 terms, but with the opposite sign in the middle. And that's just to algebraically simplify this limit to a place that we can actually apply the limit here. So if you were to do that on top, you'd get the square root of x squared times itself, which, x plus 1 times itself. So that would be x plus 1. The outside and the inside of the foiling process would go away, and that would leave you with a minus 4 for the last times the last. Then we're going to have x minus 3 on the bottom, and we'll still have that square root plus 2. So the nice thing is here, the numerator will simplify to x minus 3, which is good because that's what we're really trying to get rid of in the denominator, since that's the part that gave us 0 in the denominator. So algebraically, we can get rid of that, which is then going to leave us with the limit as x approaches 3 of 1 over the square root of x plus 1 plus 2. Now, if I directly substitute 3, we are no longer going to get an undefined value in the denominator. As a matter of fact, we get 1 over the square root of 4 plus 2. Square root of 4, of course, is 2, so we get 1/4, and there's your limit. And then for the last one, well, the last one that I can see currently, I know that there are more of them. In the case of the last one, again, it kind of follows this idea up here, in the fact that if I were to take the limit as something approaches 0 of sine of an angle over an angle, it's going to be 1. The problem is the angle is 5x. And I only have x in the denominator, but I can make the denominator a 5x. as long as I also introduce the 5 on the numerator. So I'm just multiplying by 5 over 5. I can bring the 5 from the top out to the front because it's a constant. And then that would leave me with the sine of 5x over 5x. That now follows the pattern of the same one that we had in number 1. So what we get is the 5 from the front times the limit of this piece, which is 1. So we get 5. And again, this is just kind of remembering a bunch of old limit stuff that we really haven't dealt with in a while. Number 4, don't be confused on number 4, because a lot of times people look at something like that and they're like, oh, the highest powers are in the bottom. That would be true if we were looking at a limit as x approaches infinity. This is as x approaches 2. You always still try to do direct substitution. In this case, direct substitution, 2 on the top and the bottom, while I'm not going to show it, does give you 0 in the numerator and 0 in the denominator. And you might think, well, maybe we want to factor this thing. Okay, let's do the factoring process. So the numerator would be x minus 2x minus 2, or x minus 2 squared. And then in the denominator, we'd be hoping to get an x minus 2 out of this, but then you got to try and factor a cubic. It can be done. You just have to do some long division, but one way or the other, this is not going to be fun to do. I'm not going to finish this one off. And then in the bottom one, that is one that x is approaching infinity. And the problem is the natural log of x and the square root of x both go off towards infinity at relatively the same rate. One of them does go faster than the other one, but as they start to get closer and closer to infinity, these things get really pretty close together overall. So you just have to remember, like, the square root of x would look something like that, or 2 times the square root of x. The natural log of x looks something like this. And the problem is, does the natural log of x start to cross over that square root of x, or does the square root of x stay on top so we know which one grows at a faster rate? Hard to tell. Hard to tell. But there is going to be another way to do it. So that was a lot of setup just to get to L'Hopital's rule. So what is this L'Hopital's rule thing that I would keep saying? Well, when using direct substitution, some of these times we can't evaluate the limit because it's what's called an indeterminate form. And there are 2 indeterminate forms that are going to be useful. If you end up with something that has a 0 in the numerator and the 0 in the denominator. Now remember, you cannot actually write it like that, but that's what you would end up with. Or you have some form of infinity over another form of infinity. These are what are called indeterminate forms. So the limit of the numerator gives you 0 and the limit of the denominator gives you 0, or the limit of the numerator gives you infinity, plus or minus, doesn't matter, over some other form of infinity for the limit of the denominator. Those are what are called indeterminate forms, meaning we cannot determine from this what the limit is. We've got to do some more work. You could go back and start trying to do all the stuff that we did on the first page. Instead of simplifying the expression, however, we can use this thing which is called L'Hopital's rule. Now we're actually going to define it. So once again, L'Hopital's rule says that if you get one of these 2 forms, 0 over 0, or plus or minus infinity over a plus or minus another infinity, we can apply L'Hopital's rule. So L'Hopital's rule says if I take the limit as x approaches some value, we'll call it b for now, of f of x divided by g of x, and we get one of those 2 indeterminate forms, it's the same thing as saying I'm going to take the limit as x approaches b of f prime of x over g prime of x, and then reevaluating the limit. So let me put that into slightly easier terms. If you get one of those 2 forms, you can take the derivative of the top and the derivative of the bottom separately, and then reapply the limit and see if you actually get a limit that's not indeterminate anymore. And you can keep doing that process until you actually get a limit, or you get to a place where you realize the limit is not going to exist. All right, let's actually go ahead and do some examples because, like I said, this does make things a lot easier to do overall. You do have to be able to take derivatives. So we had to kind of at least get through the derivative topic before we could do this. All right, so let's evaluate these limits using L'Hopital's rule. Now, the first thing we're going to do is, this, by the way, you should notice these are the same problems. I'm still going to go ahead and rewrite algebraically. You should always do that, by the way. If you can algebraically simplify something, you should try to do that. We're still going to rewrite this algebraically so that we simplify it to its most simplified state. So the cosines, once again, this is nothing more than what we did in the first time. The cosines are going to cancel out. And now we're left with this. If we were to apply L'Hopital's rule, and this next part for AP purposes is extremely important. Because you can use your limit laws, you would take the limit as theta approaches 0 of sine of theta, and you would take the limit as theta approaches 0 of theta. Notice I did not put a fraction bar there. Matter of fact, let me get rid of that equal sign because that is not equal to anything. This is showing that the limit of the numerator, if you plug in 0, is 0. The limit of the denominator, if you plug in 0, is also 0. Okay, you do not want to put that as a fraction because it is a non-true statement. You cannot have 0 over 0. It technically doesn't mean anything. So we're showing that the limit of the numerator and denominator are both 0. If this is a case, now we can apply L'Hopital's rule, and we just kind of abbreviate that with an L'H, just showing that we're using that. And then I'm going to write the limit as theta approaches 0. Now, L'Hopital's rule says take the derivative of the numerator and the denominator separately. It is not a quotient rule. So take the derivative of the numerator and denominator separately and then reapply the limit. So the derivative of sine of theta is cosine of theta. The derivative of theta, which is just like x, is 1. So now I can reapply theta equaling 0, plug in 0 for theta, and I get 1 over 1, or 1. And that was the limit that we had before. Okay, same principle in the next one. Again, mentally, you should be able to kind of look at that and say, okay, if I plug 3 in, I'm going to get 0 on top. If I plug 3 in, I'm going to get 0 in the denominator. So we're going to go ahead and write our steps out. The limit as x approaches 3 of the numerator is 0. The limit as x approaches 3 of the denominator is also 0. So then I can apply L'Hopital's rule, which says, don't put an equal sign there because I'm not really equaling, LH doesn't equal anything. Which says I can apply the derivative of the numerator and denominator separately. The derivative of the numerator is going to be 1/2 x plus 1 to the negative 1/2. Chain rule, multiply it by the derivative of the inside x plus 1, but that's just 1. Derivative of negative 2 is gone. Over the derivative of the denominator, which is just 1. So really, don't really need to have the 1 in the denominator, but we can leave it there. So now if I plug 3 in there, I'm going to get 1/2 of 3 plus 1, which is 4 to the negative 1/2 power. 4 to the negative 1/2 power is a square root of 4 flipped over. So that's going to be 2, so that's really 1/2. So 1/2 times 1/2 is 1/4. That was the same thing we got on the other side. It's a little bit shorter, especially if you're good with the algebra. Really makes this next one, number 3, really very simple. Again, write out limit as x approaches 0 of sine of 5x equals 0. Limit of x as x approaches 0 is also 0. Just don't write 0 over 0. Write the two limits separately. But because we did get the 0 in the numerator and denominator, we're going to apply L'Hopital's rule. So I'm going to take the limit as x approaches 0. The derivative of the numerator is cosine of 5x times the derivative of the inside, which is 5, over the derivative of the denominator, which is 1. As soon as we get a constant in the denominator, we know we're probably going to have a limit of some kind, as long as the numerator doesn't make a denominator as well, meaning it's got a negative exponent. Now we can reapply the 0. So cosine of 0 is 1. 1 times 5 is 5. Divided by 1 technically is 5. Okay. Instead of doing all the factoring, once again, you would write out your limit. I'm going to kind of skip that and just because I'm trying to save some time here. We are going to get 0 on top and 0 on the bottom. So we know we can apply L'Hopital's rule. So that means I'm going to take the limit as x approaches 2. Now, take the derivative of the numerator, 2x minus 4, over the derivative of the denominator, 3x squared minus 12. If I were to directly substitute in 2, once again, I believe that we get 0 in the numerator and we get 0 in the denominator. So that means you can apply L'Hopital's rule again. And we can keep doing it until we actually get a value, or we get infinity or something which is undefined. So I'm going to apply L'Hopital's rule again. The derivative of the numerator is 2. The derivative of the denominator is 6x. So now if I directly substitute the 2 in there, we're going to get 2 over 12, which is 1/6, and that's your limit. But again, it has to be in the form of 0 on the top, 0 on the bottom, or an infinity over an infinity, which is what we're going to run into with number 5. If we were to plug infinity into both, the natural log of x, you saw from the graph, goes off to infinity. It goes very slowly, but it does go off to infinity. The limit of 2 square root of x as x approaches infinity also goes off to infinity. So you would have infinity over infinity, which means we can apply L'Hopital's rule. So now if I take the limit as x approaches infinity, the derivative of natural log of x is 1 over x. The derivative of 2 square root of x, remember that 2 square root of x is 2x to the 1/2 power. So you bring the 1/2 out to the front. That just makes x to the negative 1/2 power. So you probably want to go ahead and rewrite this. I'm not applying L'Hopital's rule or anything yet again, but I want to write that x to the negative 1/2 is 1 over x to the 1/2. So now what I have is a fraction divided by a fraction. So we'll bring the bottom fraction up, flip it, and multiply it, which is going to give me x to the 1/2 over x. So x to the 1/2 over x is the same thing as 1 over x to the 1/2 power. And now if I were to plug infinity into the denominator, I'm going to get some form of 1 over infinity, and that approaches 0. Because the denominator would be growing faster than the numerator since the numerator is constant. It's going to approach 0. All right, I think that is plenty long enough for this first video. The second video should be a little bit shorter because there's only 4 examples, but they are what are called intermediate forms of L'Hopital's rule. So we'll come back with a short video for that one.